Most people think GPS is just that little blue dot on their phone, the one that tells them when to turn left at Starbucks. But that blue dot is only the visible tip of a massive invisible system, one that quietly keeps the modern world synchronized. 30-plus satellites orbit the Earth about 12,500 miles above us, constantly broadcasting two simple pieces of information: their location and the exact time. Your phone listens. Your car listens. Airplanes listen. Power grids listen. Financial markets listen. Now imagine something impossible. Those signals disappear. Not just for you, everywhere, all at once. In the first 10 seconds, your phone loses its map. In the first 10 minutes, parts of the global economy begin to stutter. Within hours, the electrical grid starts behaving unpredictably. And within days, supply chains, air travel, and communications begin to unravel. In 2024, GPS jamming and spoofing incidents surged by more than 400% in conflict zones, which raises an uncomfortable question. What actually happens if the world suddenly loses GPS? To understand why everything breaks, we first have to understand something surprising. GPS isn't really about where you are, it's about when you are. Every GPS satellite carries multiple atomic clocks so precise they lose less than a second in millions of years. Each satellite constantly broadcasts a timestamp. When your phone receives that signal, it measures how long the radio wave took to arrive, traveling at the speed of light. Multiply that travel time by the speed of light, and your device calculates the distance to that satellite. Do the same calculation with at least 4 satellites, and suddenly, your phone knows exactly where it is. But the real miracle isn't location, it's timing. Those timestamps, accurate down to billionths of a second, quietly synchronize much of the infrastructure of modern civilization. And the entire system is operated by the United States Space Force, with signals freely available to the entire planet. Which means something remarkable. Nearly every major system on Earth now depends on it. To grasp the scale of that dependence, look up. At any given moment, there are 8,000 to 10,000 aircraft flying over the United States alone. Globally, that number can exceed 20,000 aircraft in the air simultaneously. Modern airliners rely heavily on GPS for navigation through systems like Required Navigation Performance, which allows planes to fly extremely precise routes. Instead of navigating from ground beacon to ground beacon, like pilots did decades ago, aircraft now follow satellite-defined corridors through the sky. It's one of the reasons air travel today is so efficient. But GPS isn't just helping pilots know where they are. It helps them know where everyone else is. Lose that precision, and the entire system has to slow down dramatically. Air traffic controllers would be forced to rely primarily on traditional radar, increasing spacing between aircraft. Flight capacity could drop by up to 80% almost immediately. Thousands of flights would be delayed, diverted, or grounded. But aviation is only one piece of the puzzle. GPS timing quietly powers systems most people never think about. Take financial markets. High-frequency trading systems execute millions of transactions per second. To verify the order of those trades, exchanges rely on GPS timestamps accurate to microseconds. If those timestamps disappear, markets can't reliably determine which trade happened first. The only safe option would be to stop trading entirely. Then there's the power grid. Electricity moving across thousands of miles must stay synchronized in something called phase alignment. Power companies use GPS timing to coordinate generators across entire regions. If timing drifts by even a few microseconds, power flows begin to destabilize. And that can cascade into massive blackouts. Cellular networks depend on it too. GPS keeps towers synchronized so your phone call can seamlessly hand off from one tower to another while you drive down the highway. Without that timing signal, calls drop, networks slow, and interference spreads across the system. All because of a signal that is astonishingly fragile. Even when technology fails, humans usually step in. Pilots are trained to navigate without GPS using traditional instruments and ground-based systems. Air traffic controllers still know how to manage traffic with radar alone. Sailors can navigate using the stars. But human backup systems come with limits. They require more time, more spacing, and more caution. And when systems designed for high-speed precision suddenly revert to slower manual methods, the entire system loses capacity. Air travel slows. Shipping slows. Markets slow. The modern world doesn't stop instantly, but it begins to stumble. Another hidden vulnerability lies in how systems talk to each other. Modern infrastructure depends on perfect synchronization. Data centers must timestamp information precisely. Telecommunications networks must align signals across thousands of towers. Emergency services coordinate communications using synchronized systems. Without GPS timing, these networks begin drifting out of sync. At first, it's subtle. Slow data. Network congestion. Because once synchronization disappears, systems designed to cooperate begin interfering with each other instead. So how could GPS actually fail? The first threat comes from space itself. A massive solar storm, known as a coronal mass ejection, can flood Earth's upper atmosphere with charged particles. These storms can distort radio signals and potentially damage satellite electronics. Another threat is much closer to home. GPS signals are incredibly weak. By the time they reach Earth, they're about as powerful as a 25-watt light bulb seen from 10,000 miles away. That makes them easy to interfere with. A device that costs less than $20 online can jam GPS signals over a city block. Military-grade jammers can disrupt them across entire regions. Spoofing is even more dangerous. Instead of blocking the signal, spoofers fake it. They transmit false GPS signals that trick receivers into believing they're somewhere else. In 2024, more than 1,500 commercial flights per day experienced spoofed GPS signals in conflict regions. And there's one more threat: space debris. If satellites collide, they can create a chain reaction known as Kessler syndrome, where fragments destroy additional satellites in orbit. Suddenly, the backbone of global navigation becomes dangerously fragile. Before we continue, here's something worth thinking about. Nearly everything we've talked about so far, aviation, power grids, global trade, depends on invisible systems most people never notice. If you enjoy breaking down the hidden systems that keep civilization running, take a second to subscribe to the channel. And now, let's talk about what happens next if GPS actually goes dark. The good news is governments and engineers are starting to recognize the risk. The U.S. Navy has even begun teaching sailors celestial navigation again, using the stars as a backup. Technologists are also exploring alternative PNT systems, positioning, navigation, and timing. One promising backup is eLORAN, a powerful land-based radio navigation system. Unlike satellite signals, eLORAN transmitters broadcast extremely strong signals that are far harder to jam. Another emerging technology is quantum navigation. These sensors track motion so precisely that vehicles can determine their position without any external signals at all. And modern devices don't rely on just one satellite system anymore. Most smartphones can access signals from multiple constellations: Europe's Galileo, Russia's GLONASS, China's Beidou. These overlapping systems add redundancy, but they still rely on the same fragile concept: satellite signals from space. If GPS disappeared tomorrow, the world wouldn't collapse instantly, but failures would begin stacking on top of each other. Air traffic capacity drops. Shipping slows in crowded waterways. Financial markets pause trading. Cell networks degrade. Power grids struggle to stay synchronized. Within days, supply chains start feeling the pressure. Container ships hesitate to navigate narrow channels. Trucking logistics lose precision. Food, fuel, and medical supplies begin moving more slowly. Not because any single system failed completely, but because every system became slightly less reliable at the same time. And complex systems don't like uncertainty. Engineers are beginning to rethink how dependent we've become on GPS. Future infrastructure will likely rely on multiple timing sources, not just one. Atomic clocks inside data centers, regional timing networks, ground-based navigation systems, and satellite constellations designed with greater redundancy. The goal is simple: never allow one invisible signal to become a single point of global failure. Because GPS may be the most successful infrastructure system ever built. But like all infrastructure, it works best when it isn't the only system holding everything together. GPS is one of the greatest engineering achievements of the 20th century. A constellation of satellites quietly whispering the time from the edge of space. A system originally designed for military navigation, now guiding ships, airplanes, tractors, smartphones, financial markets, and power grids. It has made our world faster, safer, more connected. But it has also made us dependent. If those signals stopped tomorrow, we wouldn't just lose our way to the nearest coffee shop. We would lose the invisible clock that keeps the modern world synchronized. And that tiny blue dot on your phone would suddenly remind us just how much of civilization depends on signals we can't even see.